In the PCA algorithm, we take n-dimensional features and reduce them to some k-dimensional feature representation. This number k is a parameter of the PCA algorithm. This number k is also called the number of principal components, or the number of principal components that we retain. And in this video, I'd like to give you some guidelines, or sort of tell you about how people tend to think about how to choose this parameter k for PCA. In order to choose k, that is, to choose the number of principal components, here are a couple useful concepts. What PCA tries to do is it tries to minimize the average square projection error. So it tries to minimize this quantity, which I'm writing down, which is the difference between the original data x and the projected version x approx I, which was defined in the last video. So it tries to minimize the square distance between x and its projection onto that lower dimensional surface. So that's the average square projection error. Also, let me define the total variation in the data to be the average length squared of these examples xi. So the total variation in the data is, the average over my training set of the length of each of my training examples. And this sort of says, on average, how far are my training examples from the vector, from just being all zeros. So how far on average are my training examples from the origin. When we're trying to choose k, pretty common rule of thumb for choosing k is to choose the smallest value so that the ratio between these is less than 0.01. So in other words, pretty common way to think about how to choose k is we want the average square projection error, that is the average the distance between x and its projections, divided by the total variation of the data, that is how much the data varies. We want this ratio to be less than, let's say, 0.01, or to be less than 1%, which is another way of thinking about it. And the way most people think about choosing k is, rather than choosing k directly, the way most people talk about it is as what this number is, whether this is 0.01 or some other number. And if this is 0.01, another way to say this, to use the language of PCA, is that 99% of the variance is retained. I don't really want to, don't worry about what this phrase really means technically, but this phrase 99% of the variance retained just means that this quantity on the left is less than 0.01. And so if you are using PCA, and if you want to tell someone how many principal components you retained, it'd be more common to say, well, I chose k so that 99% of the variance was retained. And that's kind of a useful thing to know. It means that the average square projection error divided by the total variation, that was at most 1%. That's kind of an insightful thing to think about. Whereas if you tell someone that well, I had 100 principal components, or k was equal to 100 in 1,000-dimensional data, it's sort of harder for people to interpret that. So this number 0.01 is what people often use. Other common values will be 0.05, and so this will be 5%. And if you do that, then you go and say, well, 95% of the variance was retained, and other numbers, maybe around 90% of the variance was retained, maybe as low as 85%. So that 90% would correspond to saying this to 0.10, and so kind of parens 10%. And so range of values from 90, 95, 99, maybe as low as 85% of the variance retained would be a fairly typical range of values. And maybe a 95 to 99 is really the most common range of values that people use. And for many data sets, you'd be surprised, in order to retain 99% of the variance, you can often reduce the dimension of the data significantly still, and still retain most of the variance, because for most real-life data sets, many features are just highly correlated, and so it turns out to be possible to compress the data a lot and still retain 99% of the variance, or 95% of the variance. So how do you implement this? Well, here's one algorithm that you might use. We might start off, if you want to choose the value of k, we might start off with k equals 1, and then we run through PCA. So we compute uReduce, compute z1, z2, up to zm, compute all those x1 approx and so on up to xm approx, and then we check if 99% of the variance is retained. Then we're good, and we'll use k equals 1, but if it isn't, then what we'll do is we'll next try k equals 2. And then we'll again run through this entire procedure and check, is this expression satisfied? Is this less than 0.01? And if not, then we do this again. Let's try k equals 3, then try k equals 4, and so on until maybe we get up to k equals 17 and we find that 99% of the variance is retained, and then we'll use k equals 17, right? So that's one way to choose choose the smallest value of k so that 99% of the variance is retained. But as you can imagine, this procedure seems horribly inefficient. If we're trying k equals 1, k equals 2, we're doing all these calculations. Fortunately, when you implement PCA, it actually, in a step, it actually gives us a quantity that makes it much easier to compute these things as well. Specifically, when you're calling SVD to get these matrices U, S, and V, when you're calling SVD on the covariance matrix sigma, it also gives us back this matrix S. And what S is going to be a square matrix, and n by n matrix, in fact, that is diagonal. So its diagonal entries S11, S22, S33, down to Snn are going to be the only non-zero elements of this matrix, and everything off the diagonals is going to be 0. Okay, so those big O's that I'm drawing, by that what I mean is that everything off the diagonal of this matrix, all of those entries there are going to be zeros. And so what is possible to show, and I won't prove this here, but it turns out that for a given value of k, this quantity over here can be computed much more simply, and that quantity can be computed as 1 minus sum from I equals 1 through k of Sii divided by sum from I equals 1 through n of Sii. So just to say that in words, or just to take another view of how to explain that, if k equals 3, let's say, what we're going to do to compute the numerator is sum from I equals 1 through 3 of Sii, so we just compute the sum of these first 3 elements, so that's the numerator. And then for the denominator, well, that's the sum of all of these diagonal entries. And 1 minus the ratio of that gives me this quantity over here that I've circled in blue. And so what we can do is just test if this is less than or equal to 0.01, or equivalently we can test if sum from I equals 1 through k, Sii divided by sum from I equals 1 through n, Sii, if this is greater than or equal to 0.99, if you want to make sure that 99% of the variance is retained. And so what you can do is just slowly increase k, set k equals 1, set k equals 2, set k equals 3, and so on, and just test this quantity to see what is the smallest value of k that ensures that 99% of the variance is retained. And if you do this, then you need to call the SVD function only once, because that gives you the S matrix, and once you have the S matrix, you can then just keep on doing this calculation by increasing the value of k in the numerator, and so you don't need to keep on calling SVD over and over again to test out different values of k. So this procedure is much more efficient, and this can allow you to select the value of k without needing to run PCA from scratch over and over. You just run SVD once. This gives you all of these diagonal numbers, all of these numbers, S11, S22, down to Snn, and then you can just vary k in this expression to find the smallest value of k so that 99% of the variance is retained. So to summarize, the way that I often choose k when I'm using PCA for compression is I would call SVD once on the covariance matrix, and then I would use this formula and pick the smallest value of k for which this expression is satisfied. And by the way, even if you were to pick some different value of k, even if you were to pick the value of k manually, maybe I have 1,000-dimensional data and I just want to choose k equals 100, then if you want to explain to others what you just did, a good way to explain the performance of your implementation of PCA to them is actually to take this quantity and compute what this is, and that will tell you what was the percentage of variance retained. And if you report that number, then people that are familiar with PCA, or people can use this to try to get a good understanding of how well your 100-dimensional representation is approximating your original data set, because it's 99% of variance retained. That's really a measure of your square reconstruction error, that ratio being at most 0.01, and just gives people good intuitive sense of whether your implementation of PCA is finding a good approximation of your original dataset. So hopefully that gives you an efficient procedure for choosing the number k, for choosing what dimension to reduce your data to. And if you apply PCA to very high dimensional data sets, to like 1,000 dimensional data, very often, just because data sets tend to have highly correlated features, this is just a property of most of the data sets you see, you often find that PCA will be able to retain 99% of the variance, or retain 95, 99, some high fraction of the variance, even while compressing the data by a very large factor.